Okay, now we'll be talking about definite integrals as accumulating functions, which we've really already talked about. We're just going to do this in a more applied way. As you remember, if you have a function and you take the integral from a to wherever, b, it will calculate the area underneath that graph. But it accumulates it. So let's say we're just going from a to c. Then it would accumulate this much area. Let's say we wanted to move C further down the road, then it would keep accumulating. So it would add up all this area to the previous area, and so on and so on and so on. So it does accumulate area from left to right, if that's which way your intervals are going. On top of that, we also know that integrals undo derivatives. And if you think of a derivative as a rate of change, so it's the amount a quantity changes per time. If you integrate it, it undoes that rate, the per time part of it, and just gives you the total quantity. So that's what I wrote down here. Derivative is a rate of change of a quantity. And since integration undoes it, the integral of a derivative or a rate of change gives you the total number of quantity, the quantity left or used or whatever it is, but it's an accumulation. So it would either increase or decrease over time depending on what the graph looks like. So integrals, I hate that word, that is integrals, definite integrals will accumulate areas from left to right. So that's probably very confusing. I think I confused myself, so it's probably good to look at an example, and this should make it a little bit more clear. So here's the situation. We have a rainstorm that began at noon, and the rain was falling at a rate of, R of t is the rate function, because it says it is, of negative 0.1 t cubed plus 0.3 t squared minus 0.1 t inches per hour. So that tells you right there that it's a rate. It's an amount or a quantity per time. Also, what tells you it's a rate is it tells you it's a rate. So, believe it or not. So the question is, if given that rate, how much total did it rain from noon to 1? So we want to undo the amount per time. We want to undo the derivative by integrating. So that will undo that derivative, give us the total amount, but from here to here. So we have to figure out what here and here is. So because it says the rainstorm began at noon, noon would be our starting point. That would be where t is 0. And we're in hours, so each time we go up 1 t, that's 1 hour. So to determine how much it rained from noon to 1, we take the integral of the rate. That will give you the total amount. So negative 0.1 t cubed plus 0.3 t squared minus 0.1 t. Starting at 0, noon, ending 1 hour after it. So that would be t equals 1. And that's it. That will give you the total amount of rainfall. Don't bother doing these by hand. Do them with a graphing calculator, because that's the point isn't to show me that you can integrate. The point is that you understand that what this integration does. So, and if you don't have a graphing calculator, you can use Wolfram Alpha. I'll remind you how to do that in a second. So I already typed the function in, graph it, and then second calc 7 from 0 lower limit to 1, and it gives me 0.25. That's a nice number. 0.25. No, I'm sorry, 0.025. 0.025. And watt, 0.25 watt, it would be the amount, which is inches. So that's pretty easy. The next question, it's the same situation, but the next question, and this will be quick, is going to ask for a different time. How much rain fell from 1 to 2:30? Well, the storm still started at noon, so t equals 0 is always noon here. So we're going to, and I won't write the whole function, we'll integrate that function, but we want to accumulate the total from 1. So if t equals 0 means noon, then at 1 t equals 1 to 2:30. So 2 o'clock would be 2, 2:30 would be 2.5. There you go. Do that with your graphing calculator, or if you don't have a graphing calculator, you just type it into Wolfram Alpha, just like this. Expand that so you can see. So I just typed in integrate the function from 1 to 2.5. You can see Wolfram Alpha is nice about this. They rewrite it for you just so you can make sure that's exactly what you meant. Give you the answer. And this one's 0.25. The last one, remember, was 0.025. This one's, there's a lot more. And this would be inches. You can even see that they showed you the accumulated area. Looks like a lot, but look at the y-axis there. That's only 0.2. So, and they even give you the indefinite integral, which you're not going to need in this case, but that's it. So then the next examples I'll show you, there's one more, and then there's one more sort of more complex one, but this should be pretty easy.